Emirates Mars mission, the EMM, and the Emirates decided they want to get into space. And part of this, I think, is for education. I think a lot of it is to stimulate young people like yourselves to get interested in science and engineering and all of the things that have been important to very modern economies. So I frankly think it's a pretty good time. Now, you're from Saudi Arabia, so you're from a very rich country. You know, your country could easily decide it wanted to become a spacefaring nation, would not be a problem at all. And if so, I think then all of you would be well served and well prepared if you were ready to take advantage of that. There are a lot of new opportunities to get into space now. You know, there are all these new players. SpaceX has been very successful at launching rockets, and Blue Horizons is another one, or Blue Origins, I guess, is another one that's getting ready to launch. And so there will be a lot of opportunity. Let's see, let me tell you about my background. So when I was young, when I was your age and even younger, I loved science. I loved the idea of space and astronomy, but I didn't set out as a young person to become an astronomer. I mean, in some ways that was an accident. I loved the idea that you could explain a lot about what you see around you in the physical world by using mathematics and using experiments. So physics, pretty much. And so from a very young age, I just got interested in that, and I studied it on my own. I had a lot of fun. I studied physics on my own. I know for some people this seems kind of onerous, but I just found it kind of fascinating to see what you could do with all this stuff. And so when I went to college, I majored in engineering physics. I was actually in the College of Engineering at Cornell University, and physics was the thing I really loved. So it was essentially applied physics. And I did that as an undergraduate. And then when I went to graduate school, I went to get a PhD in physics. And my very first month there, I had to make a choice of which subfield of physics I might be interested in. And I chose astrophysics, partly because astrophysics is very broad. You have to know a lot of different physics. It's not, you know, some of the physics some of the fields, I don't know, particle physics, maybe condensed matter, you know, you really need to go deep into a particular kind of physics or specialty. For astrophysics, you're dealing with the universe. You never know what kind of physics that you need. And so you really have to learn a lot of it. I mean, you have to know a lot about quantum mechanics and atoms and molecules. You have to know a lot about electromagnetic waves and radio waves and light and, you know, just all this stuff. And if you study supernovae or stars, you have to learn about nuclear physics. You have to learn a little bit about hydrodynamics. There's just lots of stuff. So that was very attractive to me. I thought that was lots of fun. And I love to build things. So as a graduate student, I built my own equipment. I even went down in the machine shop and I, you know, cut stuff out of aluminum and bolted it together and put it on telescopes. And in those days, you could still do that very well. So I built almost all the things I used for my observations. And I just found that the life of an observational astronomer at that time was, to me, a kind of a romantic experience, because you'd go to a mountaintop, you know, you'd observe all night, you'd take data, you'd go back, you'd think about it. It was just, it was wonderful. I thought it was a lot of fun. I didn't know, by the way, when I chose this in graduate school, if I would be lucky enough or even good enough to be able to make a career out of it. Because, I mean, these things are kind of hard, at least in academia. If you want to become a professor or you want to do research, it narrows down. I mean, each step of the way from, you know, getting to college, then college to graduate school, then getting a job, and then finally getting a position at the university. You know, there are fewer of these positions available than people who want them. So you just have to be prepared for the fact that it's competitive. Now, the way I looked at it is I thought, look, I'm going to have a PhD in physics. I mean, it's a pretty valuable degree. There are lots of things I wasn't going to starve. So I didn't worry about it that much. I didn't decide that, you know, either I became a professional astronomer, a professor of astronomy, or else my life was over. I just thought, look, this is sort of a ticket that allows me to have a chance at it. And I will say that in my career, a lot of the success that came, especially early on, was certainly it was the result of a lot of hard work, but it was the result of being pretty lucky too. And I think you have to take that attitude. You have to understand that you will go through life and you will have peers, friends of yours who seem to be achieving more than you at one time or another. That's just the way, that's just the luck of the draw. That's the way life is. You can't control whether you get hit by a disease or, your family has a problem and you have to take support, or, you're just in a particularly good cohort. One year you graduate, you're very good, but everybody else is incredibly good too. And so you just can't really control that, but you can control your training and you can control your attitude toward it. And at all times, I felt it was a lot of fun. And so the fact that you're in a space club right now suggests that you guys think this is kind of fun too. And there are lots of ways that you can continue to pursue and educate yourself. And all those will be fine if they're fun and you take it seriously enough to do it well. So, I mean, it's like, if you play a sport, sports are fun, but, the people who are good also work pretty hard at it. They're competitive. So I would say the same thing is true in this business. And the other thing I'd say, when you're sort of looking at what you want to do, there are different ways in which you can do research and carry out science. Traditionally, when I was young, is half a century ago, so pretty far removed now. But when I was young, it was sort of, generally either people did experiments or observations, or else they did theory. There was a sort of a split. There were some people who could kind of do both, and they did, and they were great scientists. But by and large, people decided, and to some extent, that's a choice of what you like to do. And I know theorists who love mathematics. They're perfectly happy spending, hours a day trying to work through equations and come out with things. But, they go observing and they just think it's awful. They have to stay up all night, tired, they're working hard. They don't need that, right? Whereas there are people like me who see that kind of a thing, going to the telescope, actually making equipment work that you made and taking data and sitting there. I mean, especially on a warm summer night in Southern California, say, it's pretty nice to be out in the telescope, just watching the sky go by. To me, that was a wonderful life. So I think, when you look at the things you want to do, you should also think a little bit about what it will require you to be doing day to day to carry out research, and choose things that you think are attractive, that you would enjoy doing, that it wouldn't be so onerous to do. Having said that, I think maybe I'll pause, okay, and just let's take some questions and see what kinds of things you guys would like to explore with me.
Did you face any obstacles?
Oops, you froze, Dorian.
While you were, initially went to university? Did you face any obstacles in your first years of university, especially because you went to Cornell, which is a highly competitive school?
Yeah, but I don't think of them necessarily as obstacles. Okay, so I'll tell you, the first course in physics I took at Cornell, I got a C in. That's not a good thing to do if you want to become a professional physicist. I mean, all the other people, they were right up at the top. And so in a way, that was a bit of an obstacle. It was of my own creation, right? I mean, I was unable to do better than a C in the first course. But what I did is I sort of doubled down the second semester. Frankly, I just worked my ass off, as we say in English. I just worked really hard. I just said, I want this, and I'm just going to keep working at it, and it will come. And in fact, that's what happened. And I think from then on, I got A's in every physics course I took, and all the mathematics courses as well. But it required a lot of work. And now this isn't to me what I would call a real obstacle. So for example, in my generation, the women in my classes faced real obstacles, because a lot of the male professors were pretty skeptical of women in physics. We know at this point, this is just complete nonsense. I mean, there is absolutely no difference in terms of native ability. Now, of course, some women are better than others, just as some men are better than others, but there's no gender difference in this. And of course, in my country, African Americans, people who have very dark skin but not just dark skin. I mean, not students so much from India, but students from, say, Africa, they still face a sort of an underlying prejudice. So I would call those real obstacles. But even if you're lucky enough not to face those obstacles, even if you're given a sort of an equal shot, you will probably face challenges where you wonder if you're up to it. And I will tell you a little trick that I found, and I think this is true of almost all of the people I know who are professionals, and that is that in many of these areas, just repeated practice is what gets you good at it. I mean, we like to think, oh, it's just gift in mathematics, and certainly I know many people who are tremendously gifted this way. But a lot of what you have to do is really practice, almost like playing tennis or something. And if you work at it very, very hard, what I found is after a while, it gets much, much easier. I mean, not just easier to do, but easier to learn. You get in a kind of a zone where suddenly all the stuff you're doing is very familiar, even new concepts. You can kind of see how it works because you've worked so hard at the last one. So I would encourage you, if you face that kind of obstacle, and most of you probably will, because the stuff you're learning is kind of hard. It's abstract. It's not very intuitive in many cases. Certainly things like quantum mechanics and relativity are just completely not intuitive, but you have to learn them. Practice is what will help you, continually doing problems, working through, the kind of homework assignments. The more of that you do, the better you get at any of these subjects.
You were involved in the Gemini Imager exoplanet survey. How did you find your way to this research project?
Oh, that was an accident. I was a member of the Department of Astronomy, and I happened to, the PI of that project, principal investigator, was a good friend of mine, and he just said, would you like to get involved? And I was, at the time, I wasn't even doing research. I was a vice president for research at the Office of the President at the University of California. So my actual job responsibilities were as an executive in the California system, not so much to be a researcher. And so I thought this was a nice way to kind of dip in, and I could put a little, it was a big team. So it wasn't as if I'd let people down if I couldn't put the time in. And so I kind of got involved in it that way. But I was also quite interested in the project. They were trying to look for very young extrasolar planetary systems and see if they could characterize them well enough that they could figure out how planets were being created around other stars.
So you were a research scientist at the Space Telescope Science Institute, and now you're a professor. So do you think you have more time and opportunities to conduct research when you were at the Space Telescope Science Institute? Like, how is the freedom and what you can research currently? Are you given freedom to research whatever topic you want, or is there certain restrictions?
No, right now, if you're a tenured professor, you have infinite freedom. So for research, that's the first thing. I didn't have as much freedom at the Space Telescope Science Institute because I was the director of the institute. So it was another one of these executive jobs where, most of my attention was paid toward making sure the institute was running and carrying out its obligations as opposed to my own research. Now, we did have a research staff, and I believe that research staff had pretty much all the freedom that it needed to carry out at least astronomical research. So that was not a problem. And I don't think it was very different from being a professor. There is, I believe, an advantage to being a professor if you're a researcher. And that advantage is, it's both an advantage and a disadvantage, but that advantage is that part of your obligation as a professor is to teach. So, many people find this a distraction, but the truth is teaching well, especially if you're thinking about your subject matter, forces you to learn it much, much better than you might otherwise have done, because you have to explain it to other people. And so I think the teaching role enhances your research. It also exposes you constantly to young people. And I think that's a huge help in doing research. Now, right now, the research I'm doing, I've kind of deviated a little bit from strict astronomy, and the personal research I'm doing is into the origins of life, and it mostly involves my working in a biochemistry lab and, mixing chemicals and pouring reagents, something that I'm not very well trained to do. And I'm working with a young graduate student who, well, she's from Texas, but her family's from, I think, Pakistan or India. And she's young, she's 23, so many decades younger than I am. And I'm kind of working for her. I mean, she teaches me how to do all this stuff because she was trained already in college, and now she's helping me, and it's great. And I think, that sort of, it's a way of keeping intellectually young, to always be around young people, to always be working with students, young people like yourselves. So I do think that there's a big advantage to the university life in terms of your intellectual life. But at these institutes, a National Observatory, or at this, like the Space Telescope Science Institute, instead of teaching, your duties require, let's see, I want to make sure I bring up the chat so I answer some of those questions. Your duties require you to provide some kind of service to the observatory or the community, and that's often it's writing software, it's looking at schedules or something like that. Those things, I think, are often a little bit less, they're a little bit less helpful to you intellectually in your research than teaching might be. Let's see, let me take a look at some of the questions in the chat room. I'm sorry I've been ignoring them. So how was your experience while you were in the process of studying physics in the beginning? Was it complicated? Well, let's see what beginning means, okay? So I was so interested in physics that when I was in middle school, so I must have been, I don't know, 13 or 14 years old, I actually found one of the seniors in our high school had thrown away his physics textbook, or her physics textbook, in the trash can. And I found it and I retrieved it and I read it. I mean, I didn't, I thought, hey, this looks pretty interesting to me. I didn't have to get any grades or anything. So that was kind of complicated, but it was really, it was a wonderful experience. Then when I got to Cornell, was it complicated? The path to becoming a physicist or an astronomer, if you get into college, is usually fairly straightforward. It's hard because you have to take a lot of difficult courses and you have to do well in them, but it isn't really particularly complicated. It is entirely possible to get into the field of astronomy. I mean, to become a professional astronomer, not having been taken a strictly linear path, but it's a little bit less usual for most professionals than the more linear path. Let's see, let me do from, I just want to make sure I get all of this. So, is it true that the government released photos of a UFO? Is there evidence of any life on Neptune? Well, the government has released pictures of objects that are unidentified that seem to be in the sky. But in all cases that the government, at least our government, has investigated this, they found that it's just some fluke or natural phenomena, or easily explained, it's a balloon or something else. So weather balloons are commonly mistaken for aliens, and they're just weather balloons. So the government does that all the time. The other part of this question is there any evidence for life on Neptune? And the answer is no. That doesn't mean there isn't life on Neptune. It just means there's absolutely no evidence for life on Neptune. And I think most people who would bet on this would bet that Neptune is not a place where you're going to have life because it's just too cold. And what we know about life here is that it's the chemistry, the organic chemistry that makes all of us tick, all the reactions, all that stuff, really likes to live in a sort of a warm environment. Ice is too cold, obviously everything freezes out. Steam is no good. So liquid water, that kind of area is where you need it. And you can't really get that on Neptune. Let's see. I'm sorry, I won't try to pronounce everybody's name because I'll just embarrass myself. And let me just say, at Berkeley, we've got an incredibly diverse student population. So all of your names kind of look familiar. We've got a lot of people from the Mideast and China and all that. But the challenge for us who were raised in the middle part of America is we just don't learn to pronounce them very well. So what, let's see, what courses are taken when studying astrophysics? Well, I would say the real thing you need is you need a firm foundation in mathematics and physics. That's critical. It's good to have some knowledge of astronomy, but I will say when I got to graduate school and embarked on this career, I had not taken a single college course in astronomy or astrophysics, not one. So I learned all that stuff as I went along, and you can do that. It's not necessary to major in astronomy to become an astronomer. And in fact, there are some advantages not to doing that. Because astronomy training is thought to be a little bit more narrow toward astronomy. Whereas if you get a degree in physics or engineering physics or, even electrical engineering or one of those things, you have a much sort of a broader target, and it's easy to learn the astrophysics as you go along. Let's see. So Farah, what do you think about aerospace engineering? And if I study astronomy, what is the chance that I can be an astronaut? Well, let's see. First of all, I think aerospace engineering is great. If you like engineering, if you like building things the way I do and designing things, then that can be a very fulfilling career. Aerospace engineering does not by itself set you up to be an astronomer, but it doesn't preclude it. It gives you all the kind of background training you'd need to then learn the astrophysics and go on. Plus, there's a great premium placed on people who can build things for astronomy. It's easy, honestly, it's easier to use computers to analyze data than to actually sit down and build something and make it work. So training yourself that way has some advantages. And then the other part of the question is, what chance can I get to be an astronaut? Well, now that's a tough one, because the astronauts are not necessarily drawn from science or from astronomy or even science. I mean, a lot of the I've known a lot of astronauts because of my association with Hubble in a previous job, and half of them were military pilots. I mean, they were really trained to be fighter pilots or test pilots or, very high-end pilots. And to go into space, I mean, it's good to be able to understand the science, but it's particularly good to have a cool head in a crisis and be able to fly out of it if you need to. And so I think that's a complicated question. What are the chances? I don't know. But I do think that if Saudi Arabia, for example, was going to send astronauts to space, either through its own program or say collaborating with the United States or Russia, which I think maybe they even do, then you've got a reasonable shot within your own country of doing that. But I don't think you can necessarily train yourself to be an astronaut, because they want a diverse set of skills. Lena, can study.
I could read the questions for you.
Oh, go ahead. Sure, that'd be great.
I study IGCSE. Do I have to study astronomy in my age to go to an astronomy university?
No, but I'm not sure what IGSE is.
It's the British exam to go to school, to go to university in the UK.
Well, no, I mean, it depends on where you want to go to the university, right? So I don't know what the universities are like necessarily in the Middle East. I knew in the United States, we think the British system is pretty good. It's pretty rigorous, and so I don't think you're at any real disadvantage trying to go to an American university or U.S. university if you've got credentials through the British system. They've got superb scholarship.
So Muhdi is saying that he has a confusing question. He's studying IB physics in school, and one of the requirements is to write an extended essay consisting of some subject of your choice, but linking them all together. And he wants to choose physics, the visual arts, and English. And he's asking if it's possible to create a piece out of these three subjects.
I think it should be. Now, if you're asking me what could I do that? I don't know. I'd have to think about it a little bit. I think physics and art there are lots of ways you can do that. And I think just to take the physics and art part of it, if you look at what Leonardo da Vinci did, he was a great artist, but he also did experiments in science. And if you look at his early drawings and sketches, they have a lot of them that aren't finished, but they're just his understanding how the physical world needed to be taken into account to establish on art something that would give you the right visual impression, especially of the human body. So I think there's a lot of overlap there. As far as English, I'm not entirely sure, but here's something that you can research. There is an article. In fact, let me just see. Maybe I can put it in maybe I can send it to you. There was an article in Physics Today several years ago that talked about the difficulty people have of accepting new scientific ideas and how long it takes. So we look back on Galileo, for example, and when he first got his telescope, made his first telescope, and when he, let me just see something here. When he had his first telescope and when he realized it was very clear that the sun was the center of the solar system, it was another 70 or 80 years before that became generally accepted. We tend to think of it as happening very quickly, but in fact, it takes a long time. And I found this article, so let's see if there's a way I can send it to you. How do I send things here?
You can copy the link and paste it in the chat. And
I have a PDF file. I don't actually have the link. I'm wondering if there's a way I can.
Yeah, you can attach a file.
Okay, let me just see which menu I do. There's the chat. Here we go, file. All right, give me a second. This is a popular article in Physics Today, and you might find it interesting. So this is what I'll tell you how this works with the English in just a minute. So let me try to get this to you. Reading. Yeah, this is a PDF file of the article. And let me send this to everyone. I think I just sent it to you, Norrin. Okay, so I'm resending. So this might give you some ideas for your combination of things. And the reason I say that is because even when the scientific community knows, I mean, when I say knows, is very convinced that, okay, this is a new paradigm. And it's better than anything in the past. We don't know about the future. Even when that happens, it takes a long, long time for the general public to catch up. This isn't always a problem. It took a long time for the general public to accept general relativity, but hey, it really didn't matter very much until the first time that general relativity mattered in our lives is when the global positioning system went up. And you're not aware of it, but it turns out that the general relativistic corrections you have to make to the time standards dominate every other one of those relativistic errors. And so without general relativity, you wouldn't be able to get this phone that tells you where you are on Earth. I mean, you'd have accurate atomic clocks, but they're keeping a different time because of the gravity up there. But before that, it really didn't matter. Now, this article that I sent you is also about climate change. Now that actually matters because, I mean, if people don't accept it and say, fine, well, we'll just keep warming the planet, you know, we're getting pretty close to the time where it'll be too late. And even if you weren't convinced, you know, you will be convinced as you're baking to death in the future, your children can't make it. So I think right now there is some, a little bit more urgency. And the reason I say this is tied up in English is because it isn't the science that's the issue here. It isn't the physics. That's well understood. It's actually communication. How do you communicate this in a way that people will accept it and recognize that, you know, that we have a new set of ideas? So that's my best shot at what you can do by combining these three otherwise very disparate subjects.
But what about poetry specifically?
What about poetry?
Yes.
I'm not an expert in this. There are certainly physicists who are also poets, and I know a lot of my friends love poetry. So can you combine physics and poetry? I'm confident you can. I mean, a lot of the people, you know, both we were astronomers and physicists often do think that what we're looking at has a certain poetic or romantic quality. And I don't have the talent to write poetry about it, but there are others who do.
Lena is asking, can studying computer science or AI contribute to space exploration?
Absolutely. It's a very hot area right now. Everybody is realizing that, well, first of all, everything is pretty much driven by computers. I mean, and so understanding how they work can help you, even if your research is just writing programs for them. And in particular, for AI, or let me just say broadly, machine learning, there's a lot of interest right now in understanding how you can use machine learning for spacecraft that will, you know, you don't know what they'll encounter when they get somewhere, or you don't know if they'll be able to fix themselves, and to be able to program those spacecraft so that they heal wounds, if you like, they repair themselves, but also they react to unusual circumstances based on the learning that they had done in the past.
For anyone in the audience that doesn't know, Professor Beckwith, he led the team that created the Hubble Ultra Deep Field, the deepest visual image of the universe, and it resulted in the discovery of the most distant galaxies ever seen. So how did you have the opportunity to lead this project, and how does it feel like that, you know, generations of students will learn about this because of you?
Well, I'm going to come back to a theme that I had early on, and that is I was pretty lucky, really. I was in the right place at the right time. I was the director of the Space Telescope Science Institute at a time when we were about ready to put the most powerful visual camera on the telescope, and it would just be much more powerful than anything else anybody had done. And because I was the director, I had the power, if you like, to be able to dedicate my own director's discretionary time to a project of this sort. Now, you know, they don't give that power to someone like me so that I can just sort of throw it away. So I didn't really just say, yes, this is what I'm going to do. I went through a whole process. I consulted the community. I had a workshop at the Institute to find out if there were other things that people wanted to do. And some other things came out of that. But in the end, I kind of consulted the community and said, this is what I'd like to do. Do you think this would be okay? And they said, yes. So what I was doing this on behalf of the community, not for my own personal research. I didn't do any real personal research on it. It was just to put it out there. But it happened to be a time in history when it was possible and everybody realized it would be valuable, especially if lots of other people, students especially, got to work on the data. So I would say in many, many ways, this for me was just luck. I mean, it wasn't because I had set my whole career up to do this. I don't know. I will say though, and this is going to be true throughout your lives, luck favors the well-prepared. You will get lots of luck, good luck coming your way from time to time. And the important thing that you're doing as a young person is to prepare yourself so that when something like that comes your way, you are well enough trained and wise enough and sort of you have enough knowledge that you can take advantage of it. So I was pretty well trained. I knew how to do not just the sort of set up the science and direct the team, but to consult the community. I'd been around long enough that I recognized the need to have it as a big collaborative exercise. And so those are the sorts of things you're going to be doing with your education that it's a little hard to predict right now. You know, you'll train yourselves in physics and you should learn to write well. If all great scientists have to be able to write coherently, and the best ones write beautifully. So whatever language it is, I mean, being able to write well is important to be able to communicate. And then, you know, just to get a sense of the social norms and the cultural norms in whatever field you work in, whether it's physics or engineering or any of these other fields, so that if you find yourself in a position where you can do something like I did, you'll already have a pretty good feeling or a pretty good sense of what you need to do to make it successful. But that's true at many, many levels of life. My kids are probably older than anybody on this call. And so my kids and I were always talking this way. Now, my daughter is a scientist, so she took after me. And my son is a writer, which is a lot more like my wife. And my wife is a teacher and sort of what I would call a life coach for kids like you. She takes on private students, and you know, there's a lot of teaching, but there's also a lot of life coaching. And so we both kind of do this, and we just want to impress upon you that, you know, a lot of your learning is preparing yourselves to take advantage of opportunities. Now, I will admit, because I'm on this theme, I will give you an example of a way that I did not prepare myself well and therefore missed an opportunity. So when I was a student in high school, one of the things I was really very bad at was language, foreign languages. And even where I grew up in the Midwest, we all had to take foreign languages. And so I took French. I took years of French. I never learned French. I was just terrible. And I just thought, it doesn't matter. I'm going to be a physicist. Who cares? I don't need to learn French. So everybody kind of like, yeah, fine. Sometime later, you know, if you look at my career, I moved to Europe, and my family and I lived in Germany for 7 years. I was at the Max Planck Institute for Astronomy in Heidelberg. And so I had to learn German, and I did, and it was painful, and it took years. I was, you know, in my late 30s when I went there, and learning a language at that age is hard. I kind of did it. But then I found that as part of my job, because I was representing Germany on a council that met in Paris, I was in Paris every month for a couple of days. And I couldn't even order in a restaurant. And here I was, I'd gone through high school, I'd taken years of French. I never took it seriously. If I had been able to speak French, it would have been an enormous advantage, not just to go to restaurants, but also to speak with my colleagues from France in French, which would have been a huge political plus for me, because they would have, I mean, they might not have liked my French, but at least they would realize I was trying. So you just never know. You know, it's hard to say, oh, I shouldn't learn this or I shouldn't learn that because I'm concentrating on one thing. You just never know. I would encourage you to learn as much as you can about all sorts of things. You're never going to be sure when later in life you find a big advantage from that.
You were responsible for the Hubble Space Telescope, and you became the telescope's leading public spokesman after NASA announced in 2004 that it would no longer service the telescope, and you were successful. And no one can deny that the Hubble Space Telescope is amazing. But for you personally, what drove you to fight for its continued operation?
Well, okay. Well, first of all, let me say I wasn't responsible for the telescope. That was built by other people. I became the director. And when I was the director, I was responsible for the science program. When Sean O'Keefe, who was the administrator at the time, decided to cancel the final servicing mission, I thought it was a mistake. I thought it was a mistake for NASA. I thought it was a mistake for science. And I felt that in my position at some level, it was my job to step up and to try to preserve it. Now, there was controversy about this because we were under contract from NASA. So, you know, a lot of people would have said, don't bite the hand that feeds you. If they don't want to do it, don't let, you know, but I just took a different approach. I said, I don't think this is a good idea. I don't think it's a good idea for science or the country or even for NASA. I thought Sean O'Keefe had made a mistake. And, you know, he happened to be the administrator, just as I happened to be the director. And that was an accident of fate. And his background was in accounting, not science or space. And I thought, you know, this is just not the right guy at this time to make this decision. It's an example of how he had a certain level of luck, but I think he screwed it up because he was not prepared in that particular instance. So I decided to fight it. And I felt that was my job. Now, in the end, you know, that fight did in fact save Hubble, and Hubble is still going. And I've heard from my colleagues, it could go for another 10 years. I mean, it's doing really well. So that's great. I feel fabulous about that. For me personally, well, it was clear they were going to push me out of that job, and they did. You know, I had to resign midway in that fight, but so did Sean O'Keefe. You know, he got pushed. So it was sort of like, you know, if you read the ancient, if you read the Iliad, for example, the ancient Greek about, you know, it's like Troy. You know, in the end, all the kings and princes died. You know, and it's only a few people went off and founded Rome or did what they did. So you know, these things are not, they're not really fun. And I wouldn't want you to think it was in any way particularly heroic. It was a choice I made at the time, and I believe in it, and I think it was right. I wouldn't say that what I suffered was that bad. I mean, I'm, you know, still doing fine. Sean O'Keefe's still doing fine. And so at least in the modern world, unless you're literally going to war and you have to, you know, and the fight could result in death, I think these are, the real stakes are a little bit overblown, but it was just a personal choice about what I felt my responsibility was to my community, which is science, and to the Institute, and frankly, even to my country. I thought this was a mistake for my country.
Science rewrites textbooks all the time. What is one thing you've discovered, you know, over your career that you believe will be in the textbooks that kids learn tomorrow?
Well, let me say at the outset, that is a fabulous question. It's great. I don't know if I'm going to be able to answer it, but let me take a shot. I think within a few, maybe not a few years, but within a few tens of years, we are going to have a pretty good idea of how life originated on this planet, what the circumstances that could have led, you know, a set of abiotic, a soup of atoms and molecules that weren't necessarily cooperative to emerge as these living beings in which every molecule is cooperating with every other molecule in some magical way to create us. I think we're gonna see that. I don't know if we will discover life on other planets within that time frame. I think it's a little short because to really get good evidence of life, I think it'll probably take more than just taking spectra of exoplanets. We'll have to send probes or do something. So I think it might be a little harder, but I think that will also, will come to pass as far as rewriting the textbooks. As far as saying what's right or wrong, I think one of the more interesting questions right now surrounds the whole Big Bang Theory. The Big Bang Theory is tremendously good. It's very accurate at predicting a lot of things that we observe, which are otherwise impossible to predict. I mean, things like the ratio of the elements, how much hydrogen, helium, lithium, and so forth we have. We can calculate that from the Big Bang. Couldn't do that before. The cosmic background radiation, that's just a marvel. I mean, it almost, for all professional astronomers, that absolutely cements the case for Big Bang cosmology. And so I think we all believe that. It's a tremendously powerful theory. Nevertheless, for this theory to work, it requires a lot of stuff, that we don't know what it is. The dark matter, we don't know what that is. And the dark energy, no clue. I mean, the dark matter, at least we have some ideas of what it might be. The dark energy, no. I mean, the best we can do is that there's a constant, a factor in Einstein's equations of relativity that arise when you do Big Bang calculations, and you can ascribe that, and it has all the effects that the dark energy has. So you can say that, but I'm not sure if that lends a lot of understanding. And the fact is that both quantum mechanics and general relativity are tremendously good, incredibly precise at predicting and correctly measurements we make, in the case of general relativity on a very large scale, and in the case of quantum mechanics on a very small scale. And yet mathematically, those two theories are they don't even work together. I mean, it looks like you've got physics at a big scale and a small scale that are completely different. I think that's an enormous problem. Now, I don't see at the moment a real solution to that. I can't say, oh, well, within a few years that'll be worked out. I don't think that's true. But given the history of science and the history of human intellectual history, I have to believe that we will discover probably some new all-encompassing theory which takes account of both the large and the small self-consistently. Some sort of grand unified theory. I think we will ultimately get that. And when that happens, the textbooks will be entirely rewritten. So you have to work within that theory as opposed to the other two that we have right now. I have no, I would hesitate to make any prediction about when that would happen.
Abdullah is asking, when do you think humanity would be able to harvest large amounts of energy, supposedly enough to leave the solar system?
It depends on how you think of that. We already have done that. I mean, we've sent the Voyager spacecraft beyond the solar system. We can easily, we have rockets now. You could fire them out of the ecliptic plane. You could leave the solar system without any trouble at all. Now, that's not necessarily sending people outside of the solar system. I mean, for that, not only do you have to get them up there, but you have to give them the means that they won't die on the way. So I think it depends on what question you really want. If the question is, when do you think we'll have enough energy or enough resources to send people to the nearest stars, I don't know. I mean, it could be never. I mean, it could be we do conclude that trip just takes too long. On the other hand, we could find that, within a century or so, we'll have the ability to harness energy and, accelerate things too close to the speed of light and decelerate them later. And it will become practical to go to Alpha Centauri or the nearest stars. And so that could happen. But I don't have any prediction about when it might happen. The actual amount of energy to do something like that is not very big compared to the amount of energy we use right now just to run our societies. And I'm sure this is true. Well, right now in San Francisco, we're having a heat wave, which, for you in Saudi Arabia would probably seem like winter. But for us, if the temperature gets up above, about 30 degrees centigrade or, 80 degrees Fahrenheit, we're all going, oh, this is terrible. And so our air conditioners are going full time. We're keeping ourselves cool. We're not going out there. And I'm sure where you live, it must be much, much more severe. I mean, to live a comfortable life, even with the conditions you've got, I'm guessing a lot of you take advantage of air conditioning when it's pretty brutal. So the amount of energy it costs, to take a city like Riyadh and run it on air conditioning is probably much more than the energy it would take for one of these missions. So we've got the energy. The question is whether or not you can really concentrate it and use it in a way that you want to, and whether that's what you want to spend your money on. And I don't know the answer to that.
I've seen this all the time in lately about space tourism. Do you think that's a feasible idea, and do you think it will occur in the coming years?
Yes, I think, what's his name? The guy, Virgin Atlantic.
Elon Musk?
No, Musk, I don't know that. No, Musk has got a different idea than tourism. He really wants to colonize Mars.
Mars, yeah.
Um, probably,
Jeff, I think it was
first,
Jeff Bezos.
Richard Branson, right? With Virgin Galactic. I think
Oh, yes.
his whole business model is space tourism. So, and then I think Blue Origins, I think Jeff Bezos and Blue Origins, I think they will do some of that as well, and probably SpaceX as well. So I think you're going to see this in a few years. I mean, maybe very, very quickly. I mean, we send astronauts to the space station. If some very rich person wants to pay to go up into space and orbit a few times, I just don't see that as there's no barrier to that anymore, as long as someone will sell him the ride or hear the ride. So I think you're going to see that pretty quickly.
Lena is asking, do you think the discovery of dark matter would help Earth? How would it directly affect us as human beings?
Well, I don't know. That's a pretty good question. It's an example of how the research question is just based on curiosity. We just want to know what this stuff is without knowing if there's any practical value to it. But history tells us that this kind of curiosity-based research is often the thing that completely changes the way society works, because you couldn't have imagined beforehand what the implications are. So just to give you an example, I think it must be clear to all of you that the laser is not a sort of an incremental improvement on the light bulb. I mean, when Thomas Edison was trying out all these filaments, he wasn't doing the things that would create a laser, right? To get a laser, you needed first quantum mechanics, and then you needed people who were doing enough research into quantum molecular physics that they realized that you could get these population inversions, and maybe they could use that to create coherent life, or light, not life. And the actual invention of the laser came, I'm thinking 30 years after the invention of quantum mechanics. So it was a big lag. Now, of course, lasers play such a strong role in our lives. I mean, your lives would be totally different without the laser. I mean, from the scanners in the supermarket, and even communications with satellites, and the trivial things like pointing in a conference room. I mean, and laser surgery. I mean, there's just all sorts of ways in which lasers have completely transformed our lives. Could you have predicted that when you were researching quantum mechanics? No, nobody had any idea. So coming back to dark matter, would dark matter have any practical applications? I don't think anybody who's credible, any thinking person, thinking scientist, could make a case that understanding dark matter will improve humanity. I mean, cure disease or feed us or whatever it is you want, reduce poverty. I don't think you could make a case that it has a practical value, but that doesn't mean it doesn't have a practical value. It just means that we don't have the imagination to know what that would be, especially since we don't know what the dark matter is.
Sara is asking, is it true that there could be a possibility of existing life in Venus? I've heard that scientists have detected phosphine in the atmosphere of Venus, and the conditions there could be habitable.
Well, first of all, let me say that because we don't have because we only know of life in one context, which is us, we can't really answer the question of whether there's a different kind of life that might be in Venus, and there could be. Just because the number of possibilities for this emergent phenomena may be very, very large, and we just only see one. Now, but coming back to the phosphine experiment, I don't believe that the discovery of phosphine really points to life in Venus or the need for it at all. All it shows is there's some kind of a disequilibrium chemistry there that we don't understand. In fact, phosphine's a simple molecule. It's a phosphorus with 3 hydrogens. I mean, this is just, you don't get much simpler than that. That's in biology, that isn't even thought of much as a molecule. It's just almost like an atom, right? A real molecule is like a nucleic acid or an amino acid. And so I personally think that news story is mostly hype. Not the discovery. I think they really did discover phosphine, but I don't think it requires life. And if you read, I read several newspapers. I read the New York Times, among others. But if you read the New York Times article carefully, you will see at the end of the article, they have a citation from two biologists, one of whom is Gerald Joyce, one of the preeminent biologists in the world at the Salk Institute in San Diego. And he just said, no. He said, this is not evidence for life. This is evidence for a disequilibrium chemistry that we don't know about yet. And he's right. I completely agree with him. So you have to be very careful when you read the newspapers. You have to remember, I'm a big fan of the newspapers, right? Because you need to find out what all the bad people are doing. And the newspapers are a way of letting you know so that you're not blind. But the newspapers are in a business to sell newspapers. And so it often helps them to have somewhat sensational stories. And I think in science, you have to have take this with a little bit of grain of salt. The scientists who are saying this and the newspapers publishing it, they all have a little bit of interest in making it sound more interesting than it might actually be. I personally don't think that's a particularly profound discovery.
You've had many different professional positions. What are common skills that have helped you throughout your career that students like us could implement and try to improve on?
Public speaking. A lot of people are scared of this. I will tell you though that one of the best ways to learn to be a good public speaker is to teach something. I mean, even if you were in graduate school, I always asked all my graduate students to spend at least a year as a teaching assistant. So they had to be dealing with students and speaking. So public speaking is important. Being able to write clearly and cogently is very important. You don't have to be able to write fiction at the level of an Alice Munro, say. I mean, what you need to do is to be able to write clearly so that you don't get bogged down in jargon and other people can understand easily your line of argument. Those are skills that are important. For me personally, because I didn't just stick with a research career where it was narrow and I was only dealing with a few people in my field, I've had a lot of leadership positions. I think in the leadership positions, being sensitive to how other people think and how you can best work with them is an important skill, the people skills. And some people are just naturally good at that. Mostly the people who are naturally good at that become politicians. And everybody loves them. But as scientists, that's not our first thought. I will say, though, if you are going to be a scientist and you think you might be in a position or you might be interested in positions of leadership, and I found all these to be very interesting jobs. Every one of them for me was an opportunity and frankly, a great gift. I don't need to just be a professor. But to do that, I think you really do want to have some people skills, public speaking skills, but also just kind of empathizing with how other people feel so that as you make decisions that affect their lives, you are internally informed about how you are affecting their lives. And you're sure that you're willing to do things, even if it makes people uncomfortable, that there is a greater good reason for that.
Judy is asking, what are some interesting or useful topics in astronomy for undergraduates that aren't very common? Like subfields.
Oh, you mean subfields of astronomy?
Yeah. I'm assuming that's what she means.
I think studying the interstellar medium is kind of an interesting topic that many people don't often do because it involves a whole different kind of physics than studying, say, stars. So I think that's interesting. These days, I would say, if you're going to become a professional astronomer, you should take the time to learn general relativity. It's probably at least a full semester, if not a full year course. You don't have to do it until frankly, you could wait till graduate school. But if you have the opportunity to learn the elements of general relativity as an undergraduate, that's kind of going to be useful because with the new gravitational wave detectors, more and more events will be seen in astronomy that have to do with what you call strong field interactions, like the coalescence of black holes or neutron stars. And if you have a facility with general relativity, so you have an intuitive feel for how people come to the conclusions they do, I think that would be, that's now something that's worthwhile. I'm not well trained in general relativity. I know enough to be, I know enough to be a little dangerous. I understand the rudiments and kind of how it works, and I can explain that to students, but I can't do any calculations in it. And so that's just because of my age and background. That's just one of the things I didn't prepare myself. But I'd say that would be something that you might find worthwhile and interesting.
Farha is asking, approximately what is the percentage of space that we have discovered? Space is expanding, but what percentage have
well,
recent
it depends on what theories you believe. So the best evidence right now is that space itself is infinite, but we've only seen a certain amount of it. So anything divided by infinity is zero. So the answer to your question is 0%. We know 0% about the total universe. Now, I'm very skeptical of infinities. Infinity is a very nasty number to deal with mathematically, as you might know. And the history of physics has been that as discoveries in modern physics have come, they've made infinities go away. So for example, the special relativity or even general relativity, what Einstein discovered is that you couldn't have infinite speed, action at a distance. The speed of light limits you is finite. And if you believe it's finite and fixed, all the other infinities of this large scale stuff tend to go away. Nothing gets infinite. We don't know about the very interior of a black hole, but then that's still at the cutting edge of research. Same with quantum mechanics. You know, there you had infinitesimals. You could get things finer and finer and finer down to an infinitely small thing, and the universe was a continuum. And then with quantum mechanics, they said no. If you get down to a certain level, which is the quanta, you can't really get anything below that. That the universe is not continuous and infinitely small. It actually comes in lumps. I mean, it's lumpy, it's chunky. That's kind of what quantum mechanics says. So the history of physics tends to have discoveries which make these nasty infinities go away. And my own personal prejudice, and I'll tell you, it's just a prejudice, it's not any more than that. My own personal prejudice is the infinity of the universe will also go away at some point when we have a more sophisticated theory of either the Big Bang or how relativity and quantum mechanics actually work together.
What advice would you give us today that you wished someone gave you when you were going to college in 1970?
I would say find a mentor to help you at any stage. I mean, it could be different. You know, you have different mentors at different stages. I tended to be kind of a loner, and honestly, I think just a little arrogant. And, I can do all this stuff for myself. I kind of did, but a lot of things that I worked out were based on mistakes that I could have avoided if I had, you know, if I'd paid a little bit more attention to an older person who could give me sound advice. Now, the mentor relationship only works if you really resonate with your mentor. And, you know, you need to pick someone with whom you are kind of what the Italians call simpatico. And I don't know what that means. You know, it may be someone who's the same gender as you are. If you're a woman, maybe it's a woman. If you're a man, maybe it's a man. Maybe not. You know, it doesn't always work that way. Someone with a personality where they enjoy mentoring you. I mean, that, you know, they will enjoy talking to you and they're willing to put the time in, and, you know, you can see this as a friendly relationship. So, you know, choosing someone and actually getting that person to be willing to give their time is not trivial. But I do think that you can avoid a lot of mistakes that you would make on your own if you get some advice and recognize that one of the things that the human species has that, as far as we can tell, no other species has, is we can pass learning on, not just from generation to generation by teaching, but, you know, throughout all of history. I mean, we can read, you know, texts like the Bible or the Quran that were written centuries ago, and they still inform us about what people were thinking about back then. Whether or not you're religious isn't really the point. The point is that this is wisdom which is passed on from a long time ago. So I think taking advantage of that by finding mentors and other people, and realizing that almost at any age you can learn, just in different ways, is important. Now, at my age, I would say I'm probably learning more now from young people than from people older than me. The people older than me, I'm kind of like them. I know that. I see where they are. I know I'm going to be there in 10 years or so, but there isn't as much of a mystery to that. But because culture changes, the world changes, and it's all changes that are brought about by you guys, by the young people. Now, kind of getting attuned to how young people think and what they think their world will be, what you are going to make your world, is probably in some ways better mentoring for me than going to someone older.
Thank you so much, Professor Steven Beckwith, for giving us your time this morning. You're such an amazing person, and it's an honor that I had the opportunity, and that all of us have the opportunity to learn more about astronomy. I greatly appreciate it.
Well, Norm, thank you very much. It's always a pleasure to talk to young people, and I wish you all the most success in the world. And I think, given the strife in the world right now, I particularly like talking to students from the Mideast. There's been a lot of turmoil there, and you're the future. You're the ones who are going to decide whether or not the world is full of strife, or whether actually you'll be working together and doing science and doing great stuff. So I encourage all of you to follow your dreams.
And that's the beautiful thing about science. It brings people together even when they don't share the same culture or the same country.
It does. I mean, at Berkeley, it's very diverse. I mean, we're just, and especially in San Francisco, I mean, we're really, I wouldn't say anything goes, but you don't judge people based on their culture unless they're actively trying to undercut you. Sometimes it happens, right? But so, and it's great. It gives you just better. It's better. I mean, it's just better. You get more points of view. You get to think about it. You really learn more. You're able to, if you're exposed to a lot of diverse opinion and not just narrowly to one set. Good luck, guys.
Thank you so much.
Yeah,
you too. Thank you.
Thank you so much, Professor.
Bye-bye.
Thank you so much for your time. I really